Let me recap a bit what we did with the complex Ginzburg-Landau equation. So recall that we were aiming at an equation that generically describes a bifurcation scenario which is close to a Hopf bifurcation, where the band of unstable modes naturally connects to q equal to 0, and you have a uniform instability corresponding to an oscillatory mode. What I then showed you that by symmetry considerations, the equation describing that is this type of equation. It's called the complex Ginzburg-Landau equation, and it's always important when you see equations like so that you make them non-dimensional, so you introduce the basic length and time scales such that you get the minimal form that only contains those variables that are actually, dimensionless, and you can vary and change the behavior of the system. So it turns out, as you introduce time, length, time, and amplitude scale, that this is the equation, and you should notice that there's now two parameters, C1 and C3, and they're the only ones that change the behavior of such a pattern-forming system. Okay? All right. And then we said, well, there is a certain range of parameters where you have unstable modes. Basically, when you are below mu equal to 0, sorry, above mu equal to 0, so for mu larger than 0, you have this band of unstable modes that gives rise to patterns, and we wanted to know what kind of patterns do we get. So for that, we guessed a solution. So we said, well, let's assume that we do have solutions of the following type, where you have a complex amplitude, which is a real amplitude times a phase factor. This phase factor is a phase winding solution, so basically a plane wave. This plane wave has a dispersion, so the frequency omega that you see in the plane wave is dependent on q squared. That's important, right? Because plane waves that have dispersion have a group velocity, and that's distinct from plane waves without dispersion. The amplitude we found is 1 minus q squared. That's fine because this is exactly the bound at which r is positive. Q squared is less than 1 in this band of unstable modes. All right, and then we said, let's check whether this kind of solution is actually stable. For that, you make a perturbation and now change of notation. Capital Q is small, case q, etc. So you make a perturbation where you say the amplitude is an amplitude plus a modulation. So for that, you should think of this as the height of the pattern profile, and rho of q is how this height is changing with respect to the base solution that we have here. And here you have a variation in space where you should think of these plane waves having a modulation, so undulations or compression along the plane waves that you see there. So this is phi and rho, and they are the perturbations around the base state solution. And then after a bit of algebra, which is not too hard, what we found is that in the long wavelength limit, the dispersion relation has this characteristic structure. It has a term that corresponds to the group velocity, which is related to this dispersion relation that you see here. And then there is a instability that's characterized by a diffusion coefficient. And importantly, it's a long wavelength instability. So you see it's proportional to k squared. And you get this for k equal to 0 already. The group velocity, if you write it out, it's this combination of coefficients in the Ginzburg-Landau equation times the projection of the wave vector q in the perturbations rho and phi on the wave vector q of the plane wave. And dispersion relation for the diffusion coefficient is interesting because it has minus signs, and that means that diffusion coefficients can become negative here. And that's a very simple way of finding out when these plane wave solutions are unstable. All right? So what we did was we distinguished between the case where the wave vector q is along k and the one where it's perpendicular to k, and then these terms are either proportional to q or q squared, or they drop out. And then when you analyze the corresponding equations, this is the main finding of this linear stability analysis of a phase-binding solution. There is a line defined by 1 minus C3 C1 equal to 0, defining a dividing line such that above C1, C3, C3, C1 greater than 1, there is a transverse instability always, right? That means whatever you do here, this plane wave solution is unstable in all of the region where a pattern is possible. So a plane wave is not a solution in this domain, but of course there must be some kind of pattern in this solution because the homogeneous steady state is also unstable. We just don't know what the solution in that regime is. It's for sure not a plane wave. In the case where this combination of factors in the Ginzburg-Landau equation is less than 1, in the balloon here where you could have patterns, we find that in this gray zone you don't have a pattern given by plane waves. Again, there must be some kind of pattern. It's not a plane wave. But inside this white region, the solution that we guessed is actually a solution. So you have a plane wave solution characterized by the quantities that we calculated to begin with. All right, and this instability, where you go here from a stable band solution to an unstable instability, that's called a Benjamin-Fair instability or longitudinal instability. Right, that's how far as we got last time. Are there questions concerning that? All right, then let's continue with the analysis of that. The instability that we found here is a bit distinct from the instability that we found before. So before we had a similar type of longitudinal instability that we call the Eckhaus instability. It's very similar in terms of what the regimes are in wave vector space and mu space where you find the instability. The difference is that now our instabilities have a group velocity. So that means things can grow, right, as a perturbation, but then as they grow, they start moving. So if you look locally in space, you could have a behavior that looks like stable because any kind of perturbation that is generated is pushed away and moving away. What we would need now is a criterion under which condition you actually have an absolute instability. That means if you look at a particular point in space, when does the instability at that point in space really grow and not move away? Okay? So let me formulate that. So that's the question of absolute or convective instability. And we can actually answer this quite generally. So we assume that we have at time equal to 0 some initial condition, some kind of perturbation that you put on the system. It can be typically small perturbation around the homogeneous steady state or around the plane wave solution. And we want to know what about the stability of that. So let us calculate the solution at some later time t. Then we know that the solution at some later time t, if we are still in the regime of small perturbations around the steady state, I can write this as a linear combination, so as a Fourier transform of the initial condition phi naught of k. This is just the initial condition written in terms of its Fourier modes, and then multiplied by e to the I kx plus sigma of k t. And I'm writing it not in the most general form because I just want to illustrate to you the principle, so I'm just writing it in the case of a one-dimensional system. Okay. So phi naught of k, as said, are the Fourier modes of our initial condition. Okay, so how would we evaluate this integral here? It's not an easy integral in general, but as you look at this integral, you can also move it into complex plane. And as you move it into complex plane, you just have to make sure that you don't cross any kind of singularities. And once you move it into complex plane, you can kind of guess what the solution will be by saying this will have a solution which is significant only if there is a superposition of the plane waves that you have here that are coherent. And that's something where you say, well, let's look at those solutions where you have a stationary wave. So if we look at the stationary point to get an approximative solution, such that the dispersion relation is actually zero. In its the slope of dispersion relation is zero. Okay. Then you get as an approximate solution that phi at the point 0 t, so at the local point I'm looking at, I want to know whether the system is actually absolutely unstable. That means the amplitude grows at that particular point. Then this is proportional just to the exponential of sigma ks times t. Right, just a standard argument, I guess you have seen that, for trying to solve a Fourier transform by a stationary phase approximation. So that means there's an absolute instability if the real part of this dispersion relation, so the real part of sigma at this stationary wave vector is positive. Okay, so that's what you need to evaluate, whether that's actually the case. And you would need to do this for the particular case that we studied, namely for the dispersion relations that we have been calculating. So here, that's the dispersion relation that we found, and you need to do the algebra to figure out whether you have an absolute instability or not. All right, now having all of that, so having these kind of criteria for the transverse and longitudinal instability, having what we learned just about the absolute instability, you can plot a phase diagram. And let me guide you through this phase diagram. Just look on the left-hand side for a second, not on the right-hand side, ignore that. So as you look on the left-hand side, As promised, this will be a phase diagram as a function of the two non-dimensional parameters that characterize the Ginzburg-Landau equation, C1 and C3. C1 in the linear part, C3 in the amplitude, the coupling constant of the nonlinear part. There's this orange line here. This orange line is C1 times C3 equal to 1. And remember, that was the case such that above that line you have a transverse instability, and below that line you have the longitudinal Benjamin-Fair type of instability. Let's look below that orange line. Below that orange line, we had calculated the regime in this mu wave vector space where you have stable band solutions and where you don't. So let's pick a particular solution with a wave vector q given to us and say it's a third or something. And then you can distinguish between solutions where the winding solution, the phase winding solution, is stable. This is the blue regime that you see here. And the white regime between the orange and the blue line, that is where this phase winding solution is actually unstable, right? So those are the two lines, the orange and the blue line. Orange is this Newell criterion, and the blue line is the Benjamin-Fair or Eckhouse-like instability. All right, then there is a black line here. And this black line is just calculated using this relation, doing all the algebra. So what you find there is that in this gray zone that you have, the instability is absolutely unstable. So that means locally, as I said, the amplitude grows, while in the white regime, you see it's convectively unstable, so it grows but moves away with a finite velocity. Okay, so that's the main summary of what we have for the instabilities in that regime. The only thing that we can really say from the analysis up to now is that in this white regime, below the blue line, we have phase winding solutions that are stable. And above this blue line, there are all these kind of instabilities, and we really don't know from the linear stability analysis what kind of patterns you get in the long run. Just can't tell, because then nonlinear effects become important, and they are not encoded in the linear theory that we did up to now. So for that, you need to solve the full complex Ginzburg-Landau equation numerically. On the right-hand side, this is pretty much the same thing. It's just showing you now in the space of C3 and Q, so the value of the wave vector in the phase winding solution, when you do have unstable or stable patterns, and when is the instability convective and when it is absolute. And this is again the boundaries calculated from that relation here. For the details of this analysis, you are invited to do this in the problem set, which comes out, I guess, next week. All right, now let me talk a bit about what happens in the different phases. So here, this is a regime where we have C1, C3 less than 1. So we are in this regime where you do have a longitudinal instability, and the plane wave solution can be stable. And I picked here C1 minus 1 and C3 equal to 2. And here in this scenario, what you get is starting from an initial condition, which is just some random values in the amplitude and the phase. You start developing quite quickly a solution that's within the stability bounds, so the phase winding solution is stable. You can also see that it takes quite a while for these bands to become flat. They should have no curvature in it. That takes a long time before they lose their curvature. And you should also see that they are not flat in the sense that they're not horizontal. They're inclined. Why are they inclined? Wave has dispersion, wave has a group velocity, and that's what you see. You see the inclination, that's the group velocity of the pattern. So we have a nice plane wave solution with a group velocity. And by the way, before I forget this is a chymograph. It's a one-dimensional Ginzburg-Landau equation. Here you have space, and in that direction you have time. This is another case. So this other case here is you start your system with a plane wave solution with a group velocity that is in this band where you actually have an instability, right? So where the phase binding solution is not stable. And what then happens is this phase binding solution, which is actually unstable, survives for a while, but then it starts changing. And the way it starts changing is by having phase slips here in the plot for the phase and having these zeros in the amplitude that are co-localized with the phase slips in phi that you see there. And that's the point where actually pretty rapidly you do have this Benjamin-Fair instability where this band of plane waves is unstable and the system turns into another band of plane wave solutions. But that band now is within the stable regime of this balloon that I showed you. Okay? So you start out with something that's in the instability regime. It doesn't stay there. It becomes unstable by some kind of phase slip and amplitude singularities, and then it goes back to a solution that's a fine plane wave solution. All right. If you go further out, and that's just for you to know as a background, you can study the phase diagram of the 1D complex Ginzburg-Landau equation quite exhaustively. This was done many, many years ago by Boris Schreiman and Hugues Chatet and other colleagues. And what they particularly focused on is what happens actually when you are above this particular line of C1, C3 equals to 1. Remember, below we had longitudinal instabilities, above nothing was stable in terms of phase binding solutions. So what you find is that below this Newell line, there is no chaos. That means there's no highly irregular pattern for you. But there's some regime where C3 is large that you find some kind of intermittent behavior. So things stay of one type for a while, then they switch to another type, switch back and forth. In the regime above the Newell line, you have lots of very interesting phenomena that are extremely hard to describe analytically because they are turbulent or chaotic. And they call this phase turbulence, amplitude turbulence, and what's also called bichaos. What's meant by phase turbulence? By phase turbulence, you mean that the amplitude is fine, it looks regular, but the phase has a turbulent, chaotic-like behavior. Amplitude turbulence means that both the phase and the amplitude show some chaotic, turbulent-like behavior. Good, and you are invited. You are actually getting a Python code for the complex Ginzburg-Landau equation, and you can play with it and generate patterns like so. There's lots of things you can do with complex Ginzburg-Landau equation. It has lots of applications even nowadays. There's a beautiful review article, which is a bit aged, but it's still beautiful. It's by Igor Aronson and Lorenz Kramer when Igor was with Lorenz Kramer in Bayreuth. And they called it The World of the Complex Ginzburg-Landau Equation. It's a very nice review where if you're interested in more depth analysis, you can look into that. And you should be able to read it because I've given you the basics.